Welcome to the deep dive. Today we're looking at a really interesting research paper. It's called SageAttention3, Microscaling FP4 Attention for Inference, and an exploration of 8-bit training.
That's right. It tackles efficiency in AI attention mechanisms.
Exactly. So our mission, yours and mine, is to unpack how this work makes attention faster, specifically for generating output that's inference, and also their early work on making the training part more efficient too.
And that's crucial because attention, powerful as it is, gets really computationally heavy. That quadratic time complexity is a known bottleneck, especially for generative models.
Right. The longer the sequence, the tougher it gets.
Yeah.
So this paper brings two main things to the table.
Yes, two key contributions. First, a new FP4 attention method for faster inference, which they call SageAttention3.
Oh, right.
And second, some pioneering exploration into using 8-bit precision for attention during training.
Let's start with that first one, that SageAttention3 for inference. The core technique is quantization, right? Can you give us a quick refresher on that?
Sure. Quantization. It's basically about using fewer bits to represent numbers. It's an approximation technique to speed up calculations.
And it leverages hardware.
It does, particularly specialized hardware like the tensor cores you find in GPUs. This paper specifically takes advantage of the new FP4 Tensor Cores in NVIDIA's Blackwell GPUs.
FP4 4 bits.
Yeah.
And these are supposed to be significantly faster.
Much faster than, say, FP16. The paper actually reports a huge number for their implementation on an RTX 1590 1038 TOPS.
Wow, 138 TOPS, and they benchmark that.
They did. They claim it's a 5x speedup over the fastest available FlashAttention implementation on that same RTX 5090 hardware.
5 times faster. That's a serious jump. And they say it's like plug and play, easy to integrate.
For inference acceleration, yeah, that's the goal. Make it easy to drop in and speed things up.
But FP4 must come with challenges. Using only 4 bits sounds, well, restrictive.
It is. The paper points this out. FP4 can only represent 15 distinct values. That's a very limited range.
So capturing the full spectrum of numbers in attention calculations could be tough.
Definitely. And there's a specific issue they highlight with the attention map, the P matrix.
What's the issue there?
Well, P mostly contains very small values, often between 0 and 1. When you try to quantize these directly to FP4, the scaling factors you need.
The ones to convert back from FP4.
Right. Those scaling factors themselves need to be stored, typically in FP8 format for the hardware. But because the original values in P are in such a narrow, small range, these FP8 scaling factors also end up clustered in a narrow range.
Which means you're not using the full capability of FT8 effectively,
Right.
leading to accuracy loss.
Precisely. It's like trying to measure millimeters using a ruler only marked in centimeters. You lose precision.
Okay, so how did they tackle these FP4 challenges? The limited range first.
They developed something called FP4 microscaling quantization. Instead of trying to apply one scaling factor across a whole large matrix,
Which gets skewed by outliers.
exactly, they apply the FP4 quantization within very small 1/16 blocks. This is for the QK transpose and the PV matrix multiplications.
So you calculate the scaling factor just for that tiny block.
Yes. Find the max absolute value in that 1/16 block, scale the values down to fit FP4, do the math, and then scale back up using that block-specific factor. It contains the effect of any really large or small values.
Clever. Localizing the scaling. And what about the problem with the attention map P and its small values?
For that, they introduced a 2-level quantization strategy. It's a bit more involved.
Okay, walk us through it.
First, they normalize the values within each token's row in P, mapping them to a specific range, 0, 4, 48 by 6. This is a per token quantization step.
So you stretch out the range for each token individually first.
Right. And then, after that initial normalization, they apply their FP4 microscaling quantization, the block-based method we just discussed.
Why the 2 steps?
The key is that the first step, the per token normalization, prepares the data. It effectively spreads out the values so that when they later calculate the FP8 scaling factors for the FP4 microscaling, those factors can actually use a wider, more representative range of the FP8 format.
So it makes the second FP4 quantization step more accurate because the scaling factors are better utilized.
That's the idea. Figure 3 in the paper apparently has a nice visualization of why this helps.
Okay, those are the algorithmic tricks.
Yeah.
Did they also do things specifically for the hardware implementation?
Yes, several optimizations. One is kind of neat. They'd permute or rearrange the K matrix
Why?
to make its layout better match how the FP4 matrix multiplication hardware accumulates results. And they fuse this permutation step directly into the quantization kernel, so it doesn't add extra overhead.
Efficient. What else?
There's something called reuse shuffle, When you quantize P, you often need to find the maximum value in each row.
Right.
The online softmax calculation, which happens nearby, also needs to find those row maximums. So instead of calculating them twice.
They just reuse the ones from the softmax.
Exactly. Fusing the quantization with the online softmax avoids redundant calculations and speeds up the kernel.
Makes sense. And there was one more? Producer warp epilogue. Sounds technical.
It is quite hardware specific, but the essence is about better overlapping computation and memory operations on the GPU.
Like a pipeline.
Sort of. Instead of having the same GPU units do the math and then wait to store the result, they try to keep things busy. While one set of units, or warps, is writing results to global memory, another set can be loading the data needed for the next calculation.
Maximizing throughput by keeping the hardware busy.
Within the constraints of the registers available for this FP4 attention, yes, it improves overall efficiency.
Okay, so clever algorithms, smart hardware tuning. Let's talk results. Did it actually work? How's the accuracy?
The paper presents quite a bit of data. Table 1A compares their FP4 format, NVFP4, against another one, MXFP4. Theirs shows better accuracy for attention quantization.
Good start. And the two-level quantization for P.
Table 1B shows that it gives a clear accuracy boost compared to just directly quantizing P into FP4.
And the speed. Those TOPS numbers were high, but what about versus other methods?
Figures 4 and 5 show kernel speed comparisons on the RTX 5090. Compared to FlashAttention, SageAttention3 is shown as 4 to 5 times faster.
Wow.
And compared to another library, Xformers, it's like 8 to 11 times faster at the kernel level.
Those are just the attention kernels, though. What about, the whole model, end to end?
Good question. Table 2 looks at that. They tested it on several models, CogVideoX, Hunyuan Video, Mochi, Flux, Stable Diffusion 3.5.
And the quality impact.
The results suggest almost no loss in output quality. Pretty impressive given the speedup.
And the end-to-end speedup numbers.
Table 4a gives those. For Hunyuan Video, about a 3x speedup, and for CogVideoX, around 2.4x on the RTX 5090.
So not quite the 5x kernel speedup, but still very substantial real-world gains.
Yes, end-to-end always involves more than just the attention kernel. They also included visual examples, figures 9 through 11, 13, 14, showing the generated outputs look pretty much the same.
Okay, so SageAttention3 looks like a solid win for inference. Much faster, minimal quality hit. Let's switch gears to the second part, 8-bit attention for training. SageBlue, they call it.
Right, and this is less common ground. Most low-bit attention work has focused purely on inference speed.
So they're trying to bring similar efficiency gains to the training process itself, using INT8.
Yes, 8-bit integers. Their SageBlue approach quantizes 6 out of the 7 matrix multiplications involved in the full attention mechanism, including the backward pass needed for training.
How does it work in the forward pass during training? Is it similar to the inference methods?
Somewhat. Algorithm 2 describes it. Still have the main multiplications, S, QK, and O, PV. They do some smoothing on K and use per block INT8 quantization for QK.
Okay.
For the PV part, they found that using per token INT8 quantization on P combined with per block INT8 on V worked better for accuracy.
Different strategies for different matrices?
Seems so. And again, they reuse the max values from the online softmax calculation to avoid doing it separately. For P, equation 7 formalizes their per block INT8 quantization.
Right, that's a forward pass. The backward pass is usually more complex, right? Needed for learning.
It is. Algorithm 3 covers it, and it involves 5 matrix multiplications. Here they found something quite important.
What is that?
Quantizing one specific term, du Vaughan, that's the gradient of the output rot V transpose using INT8, significantly impacted the accuracy of the gradients calculated for Q and K.
Why that specific term?
They suggest it's due to how errors can accumulate in the backward pass, especially with the way FlashAttention structures the calculation. Quantizing that du Vaughan term early seemed to amplify errors later on.
So what was their solution? Don't quantize it.
Essentially, yes. They decided to keep du Vaughan in FP16, a higher precision format, while still using their per block INT8 quantization for the other 4 matrix multiplications in the backward pass.
A pragmatic compromise. Did it help?
Table 1C apparently shows that keeping du Vaughan in FT16 leads to much better accuracy for the DQ gradient, for instance.
Okay, so a targeted approach to maintain training stability. What about the speed and effectiveness of SageBlue overall?
Figures 6 and 7 show speed benchmarks for the combined forward and backward passes on an RTX 4090. They compare SageBlue against FlashAttention, both CDA and Triton versions, and also Xformers.
And the result?
They show SageBlue achieving up to a 1.67x speedup over FlashAttention 2.
1.67x? That's a decent speed up for training. But does the model actually learn properly? What about fine-tuning results?
That's the crucial test. Figures 8b through 8e and Table 3 show fine-tuning results. They used models like Qwen 2.5 and Llama 3.2 on standard benchmarks, GSM-8K, GDRA-P, MMLU, HeliSwag,
Yeah.
and they report basically lossless performance compared to training with BF16, which is a common baseline for mixed precision training.
Lossless fine-tuning with a 1.6x speedup. That sounds quite promising.
It does. They also mention tables 5 through 10 in the appendix show consistent results across different random Cs, which adds confidence.
What about pre-training from scratch? That's much heavier.
Yes. Figure 8a shows a pre-training loss curve. They used a 400M parameter llama model on the FineWeb80 dataset.
Did it work?
It converged, yes. But it converged slower than the BF16 baseline. Not faster, slower in terms of wall clock time to reach the same loss, it seems. This suggests their current INT8 approach might not be quite ready for optimizing large-scale pre-training directly, even if the kernels are faster individually.
Interesting. So the overall training dynamics are different. Did they show any training acceleration numbers?
Table 4b gives some data for training a 1 billion parameter llama model. Using large microbatches like 8K or 16K tokens, they saw about a 1.15x training speedup on an RTX 4090.
So some speed up, but maybe less than the kernel benchmarks alone would suggest.
Possibly. The appendix also has more detailed kernel speedups. Figures 15-18 show the forward pass kernel being around 2x faster than FlashAttention, and the backward pass kernels being maybe 1.2x to 1.6x faster.
Okay, so let's try to sum this up. SageAttention3 for inference seems like a big win, much faster generation, little quality loss, ready for deployment.
Agreed. That looks quite impactful.
And SageBroad for training is, well, it's a promising first step. It shows lossless fine-tuning with some speedup.
Yes, particularly for fine-tuning, it looks very viable. The pre-training aspect, though, seems to need more work. Convergence is slower overall, even if parts are faster.
So potential, but maybe not a universal replacement for BF16 in training just yet.
That seems a fair assessment based on their results. They do mention future work, specifically optimizing their Triton kernel implementations for SageBroad.
Which could unlock more speed.
Potentially, yes. And they also state plainly that more investigation is needed for applying low-bit attention effectively in pre-training scenarios.
Right. It's definitely pushing the envelope on model efficiency. Thanks. That was a great walkthrough of the paper.
You're welcome. It's fascinating work on a really critical component of these large models.